the relationship that we saw in the last lecture between the subgroups of the Galois group of a field extension and the subfields or the intermediate fields of that field extension hold in significant generality. And this relationship is very detailed, very strong, and is encapsulated in the fundamental theorem of Galois theory. Now, this is a big theorem. It requires some time to prove, so that's what we're going to be focused on. In this lecture, we're going to be stating and proving the fundamental theorem of Galois theory, and then doing an example where we see the relationship between the subgroups of the Galois group and the fixed fields of those subgroups. So let's go to Theorem 179, the fundamental theorem of Galois theory. All right, so let's let F be a field, which is either finite or of characteristic 0. Basically, what we need here is we need both F and any finite extension of it to be perfect. And F being finite or characteristic 0 guarantees this. And let's let E containing F be a splitting field of some polynomial in F adjoin X. Now, we're actually not going to use the polynomial that E is the splitting field of particularly. What we really need by this being a splitting field is we need the uniqueness of it. And we know that we've got uniqueness of splitting fields from previous results. Now, for the efficiency of making the statements in the theorem, let's let S, fancy S, be the set of subfields of E containing F. So all the fields which lie above F but below and below E, including both F and E at the same time. Now, we have a correspondence between the set S and the subgroups, the set of subgroups of the Galois group of E over F. For any field lying between E and F, we can construct a subgroup by taking an element K and mapping it to the Galois group of E over K. So if K lies between F and E, then any element of the Galois group of E over K is an automorphism of E that fixes K. And because F is a subfield of K, that automorphism will also be an element of the Galois group of E over F. So we've got the correspondence. Given any K, we can look at the Galois group of E over K, and that's a subgroup of the Galois group of E over F. So we've got this correspondence, and this is an inclusion reversing bijection with inverse given by the following. If we have some subgroup of the Galois group of E over F, then we can look at the fixed field of that subgroup, as we looked at last time, the set of all elements of E that are fixed by every element of the subgroup H. And so these two functions go in the two directions there. Give us a correspondence. Take a field, give a subgroup, take a subgroup, give a field. And the point is that these are inverses of each other, set theoretic inverses. And this bijective nature here shows that the relationship we had for the subgroups and the subfields that we saw last time matches up. And the inclusion reversing part of this shows why we flip the diagrams. So if we have the diagram of subgroups of the Galois group and we flip it, we'll get the diagram of the subfields of E containing F. Now, we can go further. We've got various ways that we can measure things. We can talk about the index of a subgroup inside a group. We can talk about the order of a finite field extension. And the point is that these match up according to this correspondence. So for any k in S, we have that the order of the field extension E over F is the, E over K is the order of the subgroup, the Galois group of E over K, and we have that the order of K over F is equal to the order of the Galois group of E over F divided by the order of the Galois group of E over K. This last equation here is really just a using the previous fact here along with Lagrange's theorem. Number 3 says something similar. For any H, a subgroup of the Galois group of E over K, E over F, sorry, we have that if we look at the order of the field extension of E over the fixed field of H, this is the same as the size of H, and we have that the order of the field extension of the fixed field of H over F is equal to the size of the Galois group of E over F divided by the order of H. And then finally, we have that if K itself is an element of S and is also a splitting field over F, then this Galois group, E over K, we know it's a subgroup of the Galois group of E over F, but in fact, more than that's true, it's a normal subgroup. So if K is a splitting field, then the Galois group is a normal subgroup. Galois group of E over K is a normal subgroup of the Galois group of E over F, and the Galois group of K over F is isomorphic to the Galois group of E over F modulo the Galois group of E over K. So all these things together tell us that the field extensions, which are splitting fields, have these very nice structures. That the Galois group encodes much of the field structure that goes on inside the field extension, including being able to determine the numerical measurements of the orders of the field extensions and so forth by looking at the indices of subgroups inside the group. We'll look at applications of this and how we can use this to tell things about the group later. We're now going to start looking at the proof of this. Now, the proof of this is going to take a few steps. So let's establish a few facts first. We're going to have some initial arguments, establish a couple of claims before we even start proving part 1. But once we establish these preliminary results, we'll be able to move through parts 1, 2, 3, and 4 with reasonable efficiency. All right, so starting the proof. So let's note that since E is a splitting field over F, we have that E is equal to f of a1, a2, up through an for some algebraic a1, a2, up through an over f. Thus, notice that we have the following. We have that the index of E over F, or the order of E over F, I should say, is equal to the order of E over F of A1 through AN minus 1 times the index of F of A1 through AN minus 1 over F of A1 through AN minus 2, etc., ending with F of A1 over F. We can look at the chain of field extensions from F to F of A1 to F of A1 and A2, F of A1, A2, and A3, so forth and so forth, going all the way up and up and up and up and up, and all of these are finite, since each AI is algebraic over F of A1 through AI minus 1. And therefore, the extension, when you add one more thing, is finite. This means if F is a finite field, then so is E, and so is every field K in the set S. So all K in the set S are perfect. This relies on the fact that any finite field is perfect, which is an exercise. Similarly, if the characteristic of F is equal to 0, this was the other option in our hypotheses, then the characteristic of K is equal to 0 for all K in S. So all K in S are again perfect. So under our hypotheses, every element of S is a perfect field, which we will be taking advantage of later. In particular, this means that there exists an alpha in E such that E is equal to F of alpha, that E is the smallest field containing F and just one element over E. You remember that we proved that this is the case whenever we're dealing with perfect fields. We proved it in the case that all our fields are characteristic 0, but in fact all we needed is that all the fields in play were perfect, which is the case here. In particular, this means that E is also the smallest field containing K and alpha for any K in the set S. So, with all these things set up, we want to prove two claims which will be instrumental in proving the results 1 through 4. So claim 1 says that if K is an element of S, a field lying between F and E, then the order of the Galois group of E over K is less than or equal to the index of the order, rather, of the field extension E over F. Eventually, we're going to prove that these two are equal, but for the moment, we're going to prove that just one inequality here. So, let's see the proof of claim 1. So since E is is equal to K of alpha, we have that any phi in the Galois group of E over K is determined by phi of alpha, because if we take any element of E, it can be expressed as an algebraic combination of alphas, and so if we know where alpha gets sent, then that determines phi entirely. So let's let P be the minimal P in K adjoin X, be the minimal polynomial of alpha, so that the order of E over F is equal to the degree of P. Since P has at most degree P roots, P can have at most a number of roots at most equal to its degree in E. And we have that phi of alpha is a root of P. We have to have that the number of possible elements of the Galois group of E over K is at most the number of roots of P, because phi of alpha has to always be a root of P, and phi of alpha entirely determines the automorphism phi. So we have that the order of the Galois group of E over K is less than or equal to the degree of P, which equals the order of the extension E over K. E over K. All right, so we've got claim 1 here, where we have that the order of any of the Galois group of E over K for any subfield K containing F is less than or equal to the index of E over K. What I said before was true. It's less than or equal to the index of E over F, but what really matters is that this is less than the index of E over K. Sorry about that. All right, so our first claim is that if K is an S, then we have this inequality. Claim 2 is a similar sort of inequality. So claim 2 says that if H is any subgroup of the Galois group of E over F, then the order of the field extension E over the fixed field of H is less than or equal to the order of H. So this one goes like the following. Let's suppose that H is a subgroup of the Galois group of E over F, and let's suppose that the order of H is equal to M. So now let's let alpha 1, alpha 2, up through alpha M be the orbit of alpha under H. So in other words, it's the set of all the images that you get when you take something in H and apply it to alpha. So alpha is certainly going to be one of these because the identity element belongs to H, but there could be other ones. Also, there could be repetitions inside this list. Let's let G be the product overall I of X minus alpha I, and this, at least for now, just belongs to the polynomial ring E adjoin X. So this is the product of x minus alpha 1, x minus alpha 2, etc. up to x minus alpha m. So now let's note the following. If phi is in H, then it's an automorphism of the alphas, or it's an automorphism on E, and in particular, phi is a bijection on the set alpha 1 through alpha m. Because these are the orbit under H. And so that tells us that phi bar of G, which would be the product of all the x minus phi of alpha i's, because phi is a bijection on this set, it maps each element of the set to another one. And so, in fact, what this phi is doing is just rearranging all the factors in this polynomial. And we're just going to get exactly the same polynomial back, which just gives us G. So that means that phi fixes the coefficients of G. So in particular, this means that G belongs not just to E adjoin X, but actually to the fixed field of H over X, because phi fixes the coefficient of G for any phi in the subgroup H. Also, alpha is a root of G. So therefore, the order of E over EH, remember that E is just EH, it's the smallest field containing EH and alpha. Therefore, the order of E over EH is less than or equal to, rather, the degree of G, which is m, which is the order of H. So we've got this other inequality. So that proves claim 2. So now we've got two separate inequalities that we're going to use when we go to prove parts 1 through 4 of the theorem. Okay, so let's move on and prove part 1. And I want to summarize a couple of the things that we have so far. So let's do a proof of part 1. So remember, part 1 said that we have this correspondence from S to the subgroups of the Galois group of E over F, which is given by a field maps to the Galois group of E over that field, and a subgroup maps to the fixed field of that subgroup. So the part 1 of the theorem says that this is an inclusion reversing bijection. And we're going to prove that just by showing that these two functions are inverses of each other. If we apply one and then the other, we get back to what we got, and also in the other direction. We're going to start off just by proving that this correspondence is a bijection. The inclusion reversing part of it will be easy to see after we do that. So now let's let K belong to S. We wish to show that if we take k and apply the first function, going to the Galois group of E over k, and then go the other direction, take that subgroup of the Galois group of E over F, and go to the fixed field of that subgroup, we want to show that we get the field k back. That applying one function, then the other gets you back where you started. So let's do this. If x belongs to k, then for any phi in the Galois group of E over k, we have that phi of x equals x by definition. The Galois group of E over k contains all the automorphisms of E that fix all the elements of k. So if x belongs to k, then phi of x is equal to x. And so that means that x belongs to the fixed field of the Galois group of E over k. So we have that k is a subset of the fixed field of the Galois group of E over k. That's the easy direction. For the other direction, let's suppose that A is in E and is not in K. We're not going to prove the other direction directly. What we're going to show is that what we've shown so far is that if an element is in K, then it's in the fixed field of the Galois group of E over K. Now we're going to show that if an element is not in K, then it is not in the fixed field of the Galois group of E over K, which will be good enough. Or which will prove the other inequality, really. So now we have that F is contained in K, which is contained in the field K, K of A, the smallest field containing K and A, which is all contained in E. And we have that F contained in E is an algebraic extension. So any sub-extensions of an algebraic extension are algebraic. So we have that K contained in K of A is algebraic. So now let's let Q in K join X be the minimal polynomial of A over K. Now, since A is not in K, we have that the degree of Q is greater than or equal to 2. And since K is perfect, Q has a root B, which is not equal to A. Now, it's not immediately obvious that this root B has to belong to E, so we need a little bit of an argument for that. So let's let L be the splitting field for Q rather, over E. Now, we're going to show that L actually is exactly E, but let's see how we get there. Or rather, we're going to show that B belongs to E, which is what we need. So, by Theorem 177, there exists an element phi in the Galois group of L over K, such that phi of A is equal to B, because they are the two roots of an irreducible polynomial. Now, furthermore, since A belongs to the set E, which is the smallest field containing F and A1 through AN, what this means is that A is a rational expression of the AI, and so is B, because we have that the function phi will fix the elements of K, and hence fix the elements of F, and will just permute the elements A1 through AN. So B is also an element of this field containing F and A1 through AN, which is E. So that means that by theorem 177, we could in fact find an element of the Galois group of E over K, which sends A to B. So we have that phi is an element of the Galois group of E over K, and phi of A is equal to B, which by construction is not equal to A. In particular, this means that A is not in the fixed field of the Galois group of E over K. So we assumed that A was not in K. We showed that it's not in the fixed field of the Galois group of E over K. And so that means that we have that K is a superset of the Galois group of E over K, and hence we have that K equals the fixed field of the Galois group of E over K. So this shows that if we take a field, we look at the Galois group of E over that field, and then we take the fixed field, then we get back to the original field we started with. So now let's go the other direction. Let's start with a subgroup, look at its fixed field, and then look at the Galois group of E over that fixed field and show that we get the same subgroup. So now let's let H be a subgroup of the Galois group of E over F. We wish to show that H is equal to the Galois group of E over the fixed field of H. So let's let phi belong to H. And then for any x in EH, we have that phi of x is equal to x by definition. And so that means that that phi is in the Galois group of E over EH. So we certainly have that H is a subset of the Galois group of E over EH. Now, to get the other direction, we're going to use our two claims that we worked before. Now, by claim 2, we have that the order of H is greater than or equal to the order of the field extension E over EH. And by claim 1, we have that the order of E over EH is greater than or equal to the order of the Galois group of E over EH. So that means that the order of H is greater than or equal to the order of the Galois group of E over EH. but we already showed that H is in fact a subset of the Galois group of E over EH, so they must be exactly the same. So that means that we must have that H is actually equal to the Galois group of E over EH. So that shows that the functions that take a field K to the Galois group of E over K and the function that takes a subgroup of the Galois group to the fixed field of that subgroup are set theoretic inverses of each other, which means that these two sets sit in bijection with one another. The inclusion reversing is fairly easy to see. So let's suppose that we've got fields K and L sitting between F and E. Now, if phi belongs to the Galois group of E over L, then phi fixes every element of L, hence of K. So that means that phi will belong to the Galois group of E over K as well. So this means that we will have that the Galois group of E over L is a subset, actually a subgroup, of the Galois group of E over K. So that shows the inclusion reversing in the one direction. For the other, let's suppose that H is a subgroup of J, which is a subgroup of the whole Galois group of E over F. And now, if X belongs to the fixed field of EJ, then that means that phi of X is equal to X for all phi in J. So that means that phi of X is equal to X for all phi in H, since H is a subset of J. So that means that X belongs to the fixed field of EH. Hence, we have that the fixed field of J is a subset of the fixed field of H. So this shows the inclusion reversing part of the bijection. All right, so that finishes part 1 of the statement of the proof. Let's move on to part 2, which connects up the indices of the subgroups of the Galois group with the degrees of the extensions of the fixed fields corresponding to them. So let's recall what we're trying to prove in part 2. We're trying to prove that for any k belonging to this set S, we have that the index of the extension E over K, or the order of the extension rather, is equal to the order of the Galois group of E over K, and the order of the extension of K over F is equal to the order of the Galois group of E over F divided by the order of the Galois group of E over K. Let's see how we do this. And once again, we're going to use the claims that we described before. So let's let K be a field lying between F and E. And by claim 1, we have that the order of the extension E over K is greater than or equal to the order of the Galois group of E over K. So that gets us halfway there. And now by claim 2, we have that the order of the Galois group of E over K is greater than or equal to the order of the extension E over the fixed field of the Galois group of E over K. So this is just claim 2 with the Galois group of E over K taking the place of the subgroup H. But now by part 1 of the proof, we have that the fixed field of the Galois group of E over K is exactly K. So this means that the order of the extension E over the Galois group of E over K is actually equal to the order of the field extension E over K. So we have that the order of E over K is greater than or equal to the order of the Galois group of E over K, which is greater than or equal to the order of the extension E over K. So we have equality throughout, and the first part of part 2 is proved. Now, the second part is pretty much just using previous results that we have combined with the above statement. So now by theorem 173, we have that the order of E over F is equal to the order of E over K times the order of K over F. This is just what we've noted before, that when we have an extension of an extension, the order of the big extension is the product of the two small extensions inside. So this means that rearranging, we have that the order of K over F is equal to the order of E over F divided by the order of E over K. But now applying the first part, the order of E over of the extension E over F is equal to the order of the group, the Galois group of E over F, and the order of the group, the order of the extension E over K is equal to the order of the Galois group of E over K. So we can determine the order of a field extension simply by measuring the size of the Galois groups involved, which are actually easier to handle most of the time. So now for part 3, we're trying to show that for all subgroups of the Galois group of E over F, we have that the order of the extension E over the fixed field of H is equal to the order of the subgroup H, and the order of the fixed field over F is equal to the order of the Galois group of E over F divided by the order of H. This is almost saying exactly the same thing as part 2. So for the proof of part 3 here, we can let H be a subgroup of the Galois group of E over F. Now by part 2, we have that the index of E over EH is equal to the order of the Galois group of E over EH. And by part 1, we have that the Galois group of E over EH is exactly equal to H. So that shows the first part immediately, that the order of the field extension E over EH is just the order of the subgroup H. So by part 2 again, we have that the order of EH over F is equal to the order of E over F divided by the order of E over EH is equal to the order of the Galois group of E over F divided by the order of H. All right, so basically 2 and 3, parts 2 and 3 of the theorem allow us to connect up the numerical measurements between the subgroups, the net of subgroups of the Galois group, and the net of subfield extensions. Now, part 4 is going to take a little bit more work than parts 2 or 3 did. And it says that if K contained in S is a splitting field over F, then the Galois group of E over K is a normal subgroup of the Galois group of E over F, and that means that we can take their factor group, and in fact their factor group is going to be equal to, or isomorphic to, the Galois group of K over F. So the Galois group of K over F is isomorphic to the Galois group of E over F over the modulo the Galois group of E over K. All right, so let's do this. Again, we're going to do it in 2 parts. There's 2 things to prove here. First, that the Galois group of a splitting field is going to be normal. Not every the Galois group of every field is not necessarily going to be normal, but the Galois group of a splitting field is going to be normal, and in this case we can construct the Galois group of K over F. So let's look at the proof of this. So let's let K be the splitting field of some little f inside the polynomial ring over the field F. Now let's let B1, B2, up through Bm be the roots of little f in K, or in E rather, or also in K, so that we have that K is equal to f of B1, B2, up through Bm, the smallest field containing f and these roots. Now, given any phi in the Galois group of E over F, we have that for any I, phi of Bi is a root of little f. We've seen this before, that any element of the Galois group must permute the roots of any polynomial over the lower field. So phi bi is a root of f. So thus, phi is a bijection on the set B1 up through Bm. And hence, we have that phi of K equals K. So this is what's important about splitting fields. If I just take a random field that lies between F and E, and take some element of the Galois group of E over F, that phi might send things in K to something outside of K. But when K is the splitting field of some polynomial, that's not going to be the case. So that's what we're showing here, is that given any splitting field of F and any phi inside the Galois group of E over F, phi of K is equal to K. This is what is going to make the Galois group here of E over K be normal. So that's what we're going to prove now. So let's let phi be in the Galois group of E over K, and let's let phi be in the Galois group of E over F. Now we claim that Phi psi phi inverse is in the Galois group of E over K. This is what we need to prove in order to show that the Galois group of E over K is normal. So let's let X be an element of K, and let's let Y be an element of K such that phi of Y equals X. We know this is possible because we know that phi of K is equal to K. So now we have that phi psi phi inverse of X is equal to phi psi of Y. Because phi of Y is equal to X, so phi inverse of X is equal to Y. Now psi belongs to the Galois group of E over K, which means it fixes every element of K, which means phi of Y is just Y. Psi of Y is just Y. And now phi of Y is equal to X, which is what we went for. So therefore, we have that phi psi phi inverse belongs to the Galois group of E over K. Hence, we have that the Galois group of E over K is normal inside the Galois group of E over F. All right, so we've got the normality. We now have to move on and prove this isomorphism. Now we're going to use the first isomorphism theorem for groups. When we do that, when we've done it in the past, most of the time, figuring out the kernel of the homomorphism has given us more work to do, and the surjectivity of the homomorphism we work with has been easier. It's going to be reversed here. We're going to construct a homomorphism to use with the first isomorphism theorem, and determining that it is surjective is actually going to be the hardest part of the process. So we're trying to show that the Galois group of K over F is isomorphic to the Galois group of E over F modulo the Galois group of E over K, now that we've shown that this subgroup is actually normal. So let's let tau be a function from the Galois group of E over F to the Galois group of K over F. Be given by tau of some function, some automorphism phi, be restricted to K. So this notation means that phi restricted to K is the function that has the same outputs as the element phi. Its domain has just been restricted to K. So we had an automorphism on E. We're now getting an automorphism on K. And by the first part, since phi of K is equal to K, we definitely have that phi is where we want it to be. It's an automorphism on K. And because the original function, or tau of phi, because phi fixed the elements of F, tau of phi, which is just the restriction of phi to K, is also certainly going to fix the elements of F. Now, it's easy to see that tau is a ring homomorphism. Restriction of functions, you're not really doing much. You're sort of just narrowing your gaze, and so nothing can really go wrong. The restriction of a composition is the composition of the restrictions. Sorry, not a ring homomorphism. Sorry, group homomorphism, of course. So now we want to show that tau is surjective and that its kernel is what we want on the bottom of the this factor group. So let's suppose that psi is in the Galois group of k over f. We're going to show that psi is in the image of tau, that there's something in the Galois group of E over F that gets mapped down here to psi. So now we have that E is a splitting field for K in two different ways. So we had that K is just a subset of E. But we could also take K, map it to K via psi, and that K is also a subset of E. And E is going to be a splitting field for K in both of these ways. But we know that we have a uniqueness of splitting fields. So by the uniqueness of splitting fields, which is Theorem 162, there exists a K extension field isomorphism phi from E to E up here, such that for all x in K, we have that phi of x is equal to psi of x. In particular, this means that phi restricted to K is equal to psi. So that means that psi is equal to tau of phi. So hence phi is, hence tau, rather, is surjective. All right, so finally we need to know about the kernel of tau. So an element phi is in the kernel of tau if and only if the identity homomorphism on K is equal to tau of phi, but remember that tau of phi is just phi restricted to K. And so this happens when phi is in the Galois group of E over K, when it fixes the elements of K. So by the first isomorphism theorem, we have that the Galois group of K over F is isomorphic to the Galois group of E over F modulo the Galois group of E over K. So that finishes the fundamental theorem of Galois theory. Now, Galois theory can be used for a host of different theories and be developed for understanding lots of different kinds of situations in field theory. We're just going to do one example here, and in the next lecture we're going to talk about how we can use it to understand solvability of polynomials by radicals. But I want to mention that there's a whole lot more that can be done with Galois theory than we're going to have time to cover here. But let's look at an example of how we can use Galois theory to understand the extension, an extension field. So let's let E be a subfield of C, be the splitting field, the polynomial p, which is x cubed minus 2, which is a polynomial over the rationals. So it's the smallest field in which this polynomial splits completely. So letting omega be the primitive third root of unity, which is negative 1/2 plus the square root of 3 over 2i, primitive cube root of unity, we have the following three elements are roots of p. We have alpha 1, which is the cube root of 2, alpha 2, which is the cube root of 2 times omega, and alpha 3, which is the cube root of 2 times omega squared. And these are the roots of p in C. So we have that the field E is the smallest field containing the rationals, and alpha 1, alpha 2, and alpha 3. We have that the Galois group of E over Q is given by the permutations of alpha 1, alpha 2, alpha 3. Now, in this case, the reason why we know that the Galois group is exactly given by the permutations of alpha 1, alpha 2, alpha 3 is a combination of theorems 177 and 178. Theorem 177 says that if you have two roots of a primitive of an irreducible polynomial, such as p, then there always exists some element of the Galois group that permutes those. So there has to be something that takes alpha 1 to alpha 2. There has to be something that takes alpha 2 to alpha 1. But Theorem 178 says that those are the only permutations that are possible, because any element of the Galois group of E over Q must send a root of P to another root of P. So those two combined tell us that the Galois group exactly corresponds to the permutations of alpha 1, alpha 2, and alpha 3. So we can tell right away that the Galois group of E over Q is isomorphic to the symmetric group on 3 elements. And we can write down this isomorphism explicitly. And I'm going to write down the permutations here on the left. 1, 2, 1, 3, 2, 3, 1, 2, 3, and 1, 3, 2. These are the elements of S3. And these correspond to elements of the Galois group, which I'm going to notate as follows. First of all, the identity permutation, which doesn't change anything, is just going to correspond to the identity homomorphism, automorphism on E, which sends alpha 1, alpha 2, and alpha 3 just to alpha 1, alpha 2, and alpha 3. Now the permutation 1, 2 is going to go to the automorphism phi 1, 2, which is going to send alpha 1 to alpha 2, alpha 2 to alpha 1, and is going to leave alpha 3 alone. Phi 1, 3 is going to be the automorphism that sends alpha 1 to alpha 3, and alpha 3 to alpha 1. Phi 2, 3 is going to send alpha 2 to alpha 3, and alpha 3 to alpha 2, and leave alpha 1 alone. And then we have two more which sort of cycle the roots of P. So we have phi 1, 2, 3, which sends alpha 1 to alpha 2, alpha 2 to alpha 3, and alpha 3 to alpha 1, and phi 1, 3, 2, which cycles them in the opposite direction. Alpha 1 goes to alpha 3, alpha 2 goes to alpha 1, and alpha 3 goes to alpha 2. These are the only automorphisms of E which fix the elements of Q. So we can look at the net of subgroups of the Galois group, which are just the subgroups of S3, and look also at the indices of their subgroups, and then use the Galois group, use the fundamental theorem of Galois theory to tell us what that means about the subfields that lie between the rational numbers Q and the field E. So we can look at the net of subgroups of S3. We have the Galois group of E over Q up here. We have the identity elements. I should say here the net of subgroups of the Galois group of E over Q. And then we've got three subgroups of order 2. We've got the subgroup generated by phi12, subgroup generated by phi13, and the subgroup generated by phi23. These are the three subgroups of order 2 in the field, or in the subgroup, in the group, the Galois group E over Q. Each of these phi12s, phi13, phi23, each of these is their own inverse. And so the subgroup generated by each of them is of size 2. And then we have the subgroup phi12 generated by phi123, which has 3 elements. It has this cycle, the other 3 cycle, phi132, and the identity element. So this is 3. Now we know that the size of the group is 6, and so we know that the subgroup of order 2 must have index 3 inside the whole group, and similarly for the other groups of order 2, and then the subgroup of order 3 must have index 2 inside the whole group. Now, in order to use this to construct the net of subfields of E over Q, we want to know what the fixed fields are of each of these subgroups. So let's start working on that. Now, the fixed field of the identity element is just the whole field itself. Now, the identity element fixes everything, and so the fixed field of E is just E. Now, the fixed field of the whole Galois group is just Q itself. Now, we want to look at some of the other ones, the ones not at the extreme. So let's try looking at the fixed field of the subgroup generated by the automorphism phi12, which sends alpha 1 to alpha 2 and alpha 2 to alpha 1. So this is going to be the set of all elements x in E such that phi12 of x is equal to x. So now, by the fundamental theorem of Galois theory, fundamental theorem of Galois theory, we have that the order of the fixed field of the subgroup generated by phi12 over Q is equal to the order of the Galois group of E over Q divided by the order of the subgroup generated by phi12. Well, the order of the Galois group is 6, the order of the subgroup generated by phi12 is 2, and so we have 3. So we know that when we're looking for the fixed field of phi12, we're looking for a field extension of order 3 over the rationals. So we have that E phi12 is a 3-dimensional Q vector space. Once you know this, a lot of times there's a natural guess as to what it might be. So we might guess that this fixed field will just be the field Q of alpha 3. Now, we might guess this very naturally because phi 1, 2 already fixes alpha 3. And so we know alpha 3 is going to be contained in this fixed field, but we can go further than that. So note that Q of alpha 3 is a vector space with basis 1, alpha 3, and alpha 3 squared. And this is because the minimal polynomial of alpha 3 has degree 3. So this we definitely have a vector space with the correct dimension, with dimension 3. Also, we have that phi 1, 2 of alpha 3 is equal to alpha 3. So alpha 3 is certainly contained in the fixed field of the subgroup generated by phi 1, 2. So since alpha 3 has to belong to this fixed field, so does alpha 3 squared. And so we must have that Q alpha 3 is a subset of the fixed field of the subgroup generated by phi 1, 2. And in fact, because these two subfields have the same dimension over Q, dimension is Q vector spaces, so they both have Q dimension 3. So we have that Q alpha 3 is actually equal to the fixed field of the subgroup generated by phi 1, 2. So there we go. By completely symmetric arguments, just changing the roles of 1, 2, and 3, we can get that the fixed field of phi 1, 2 is equal to Q of alpha 3. The fixed field of Q2, 3 is equal to Q of alpha 1. And the fixed field of Q 1, 3 is equal to the fixed field of alpha 2. Sorry, is equal to Q of alpha 2, smallest field containing Q and alpha 2. So there's one more subgroup that we need to find the fixed field for. We need to find the fixed field of phi 1, 2, 3. Now, the automorphism phi 1, 2, 3 doesn't fix alpha 1, alpha 2, or alpha 3. However, we do know that this fixed field has to be something. It can't just be Q, because we have that the order of the fixed field of phi 1, 2, 3 over Q is going to be equal to the order of the Galois group of E over Q divided by the order of the subgroup generated by phi 1, 2, 3, which is equal to 6 over 3, which is 2. So we know that this fixed field is going to be a two-dimensional vector space over Q. This means that this fixed field will contain a basis of 1 comma beta over Q, where beta is some element of E, and because 1 beta has to be a basis over Q, we must have that beta squared belongs to the span of the elements 1 and beta. And in fact, we can guarantee that this has to just lie in Q. So we're looking for something that, an element beta whose square is in Q. Well, this means that beta has to be equal to C times I for some real number C. Because if the square of a complex number is real, then it had to have been real to begin with, or a purely imaginary number. So we can try around with a number of ways of constructing things, and you pretty much just have to try things. But you can notice that we've got that omega is -1/2 plus the square root of 3 over 2i, and omega squared is actually -1/2 minus the square root of 3 over 2i. So in particular, this means that the square root of 3 over I is equal to omega minus omega squared. Now, omega by itself doesn't, it's not one of alpha 1, alpha 2, or alpha 3, but you can notice that omega is actually equal to alpha 2 over alpha 1, because alpha 1 is just the cube root of 2, alpha 2 is the cube root of 2 times omega, and similarly, omega squared is just alpha 3 over alpha 1. So we can get an element which is purely imaginary as a rational combination of the alpha 1s, alpha 2s, alpha 3s. This definitely belongs to E. But in order for this to work for us, we need to show that this element belongs to the fixed field of phi 1, 2, 3. So let's let beta equal alpha 2 minus alpha 3 over alpha 1. So then we certainly have that beta squared will be the square root of 3i squared, which is -3, which definitely belongs to Q. And we have that phi 1, 2, 3 of beta is equal to phi 1, 2, 3 of alpha 2 minus alpha 3 over alpha 1. So this is going to take each of the alphas and shift it one index further. So phi of alpha 2 becomes alpha 3, phi of alpha 3 becomes alpha 1, and phi of alpha 1 becomes alpha 2. So let's see what this does for us. It's not clear that this is equal to beta, but we can try. So alpha 3 over alpha 2 and alpha 1 over alpha 2, we can write down alpha 3 was the cube root of 2 times omega squared. Alpha 2 is the cube root of 2 times omega. Alpha 1 is just the cube root of 2, and alpha 2 is the cube root of 2 times omega times omega. Simplifying this down, we get omega minus omega inverse, which is exactly what we want when we realize that because omega cubed is equal to 1, omega inverse is the same as omega squared. So this means that beta belongs to the fixed field of phi 1, 2, 3, and hence the fixed field of phi 1, 2, 3 is going to be Q adjoin beta, where beta is this omega minus omega squared, cube root of the square root of 3i. So now by inverting the net of subgroups that we had before for the Galois group of E over Q, we can write down the net of subfields of E over Q. So we had before, at the bottom, we had the identity. the trivial subgroup containing just the identity homomorphism. That's going to flip up here. The fixed field of the identity homomorphism is just E. Up at the top, we had the whole Galois group. The fixed field of the whole Galois group down here is Q. And then we have the fixed field of phi12, which is Q alpha 3. The fixed field of Q13, which is Q alpha 2. The fixed field of phi23, which is Q alpha 1. And then the fixed field of phi123, which is Q of beta, which is, we'll just go ahead and write as the square root of 3 times I. Now, the orders of these field extensions are all equal to the corresponding indices of subgroups that we had before. Now, remember that things are flipped here, and so we've got 2, 2, 2, 3 here, and 3, 3, 3, 2 here. And so the thing that, one of the main things that Galois theory does for us that is maybe a little surprising is not necessarily coming up with these subfields. We could have come up with these subfields fairly easily, even calculated the indices, or the orders of the field extensions, rather. But what Galois theory tells us, which is not at all obvious from just looking at this from a field perspective, is that these are the only fields that lie between Q and E. There are only 4 fields that lie strictly between the rational numbers and the splitting field of x cubed minus 2. So this was the splitting field of x cubed minus 2. This is this is interesting for us. A lot of times when we deal with things in algebra or mathematics in general, there are infinitely many things that we can look at. We say there are infinitely many numbers between any 2 given numbers. There are infinitely many degrees of polynomials that we could look at. Infinitely many polynomials of a given degree much of the time. But when we're looking at Galois theory, when we're looking at splitting fields of polynomials, all of a sudden things come way, way down, and Galois theory can show us that the structure of field extensions is basically the same as the structure of subgroups. And so it's much more tractable than it initially appears. And if you want to prove something about every subfield of this field E, well, you only have 5 fields to work with, or 6 fields to work with, including E itself. So this is where a lot of the power of Galois theory can